Welcome back. Last time I left you with this example. I said assign whether we have identical structure, the constitutional isomers, or stereo isomers. In order to answer this actual question, I'm going to practice some example for you, and then we will go after it. Here we have butane. Butane, it has 4 carbons, and it says CH3, CH4, H10, or CH3, CH2, CH2, CH3. Okay. If you look to this molecule through this bond, the bond between carbon number 2 and carbon number 3, you will get at least three different structures. The first structure, we have a 1-methyl is pointing up, and the second is 180 degrees far from each other. In that case, we say the dihedral angle is 180 degrees. And which dihedral angle? Okay, the angle between these two substituents. Okay, so this angle is going to be 180 degrees. Okay, so I'm talking about technically that theta. And what do we name this one? This one, we call it anti structure. It's staggered. Okay. Staggered and is anti-staggered conformation. And the next one is that 2 methyls are 2 methyls are 60 degrees far from each other, and the name for it, again, this is going to be a staggered structure, but we call it gauche. Okay. So it's staggered and gauche as well. And the third example, you have the methyl groups in 60 degrees far from each other. The dihedral angle is 60, so it will be gauche. And again, it will be staggered conformation. Okay, now a question is, what's the difference between this, 3 technically structures? The difference between them, we decided to move the second carbon, okay, move it by 120 degrees. So we rotate, okay, we had rotation around this technically, we had a rotation around this bond. Okay, around the carbon, the bond between carbon number 2 and carbon number 3. And through that rotation over a single carbon-carbon bond, we managed to get 3 different structures. Okay, and so the question is going to be this: can those compounds be inverted by rotation about a single bond? Okay, single bond. In this case, yes, we managed to get 3 structures through rotation. Okay, and now what should I call them? I'm going to call them conformational isomers. Okay, so there are isomers that we got them through rotation around a single carbon-carbon bond. Okay, now let's get back to the example that we were practicing. Okay, here we have OH in equatorial, and it's pointing up. The second one, we have OH in axial position, and it's pointing up. Let's take the first one. So the first structure is going to be this. And we have OH in this position. And we're going to do ring flip. If we do ring flip, this part of the molecule will go down. Okay, and that one will be pointing up. Okay, so I'm going to do ring flip, and that one, forgive me. Very good. Okay, so this one now is pointing up, and OH, sorry, the second side will be pointing down. Okay, where is OH? Okay, OH used to be in equatorial position, and it's pointing up. Okay, so you're gonna say whenever we do ring flip, the equatorial will turn to axial. Okay, but Okay, but the up stay up and down stay down. You're not going to change those. And also, we said equatorial is turning to axial or axial. Okay, or you can say here axial will turn to equatorial. So those two are going to happen whenever you have ring flip. Okay, I'm going to show the OH. OH, I want it to be in axial position. Let's zoom on this region. Okay, and that one. Okay, in that one, that position, I have H here. I can have H here, axial position, and the equatorial, it will be down. Okay, so it will be down. Okay, now I want OH to be pointing up, and the only position that is pointing up is here. So I'm going to put the OH there, and OH is going to be here. And OH is going to have axial position, and it's pointing up. Okay, how did I get this structure? I did it through ring flip. Now, what's the relationship between these two structures? We got them through rotation, not rotation, technically from bending, okay, from bending. We did not break any bond, okay? We did not break any bond. The connectivity is still the same. And the only way, like the way we got it, structure got bented and rearranged itself in a space, okay, in a space. So I got two isomers, okay, and the difference between them, we got them through ring flip. I'm going to call them conformational isomers. Yeah, isomers that they can get converted to each other. And because I keep saying they can get converted to each other, I need to show the second arrow, and that second arrow is pointing back because these two, they can get converted to each other. Okay, so now what's the relationship between those two structures that I mentioned? The answer is going to be they are conformational isomers. Okay, very good. So now that we got the idea how to differentiate stereoisomers from constitutional isomers, we're going to zoom on stereoisomers. Okay, first concept that we need to know, what's the meaning of chiral molecule? In order to have chiral molecule, you need to have some mirror image. Okay, you need to have some mirror image that they are not superimposable. Okay, superimposable. Like what? Okay, my hands, they are mirror image of each other. Okay, you might say, oh, they will sit each other perfectly. No, okay, they're not going to see. Okay, they're not going to sit perfectly on each other, and this is the reason for it. Okay, when you put the mirror, okay, so this is my hand and the left hand. When I put the mirror here, this thumb, it will be close to the mirror. Okay, close to the mirror. And okay, now the right hand clearly is mirror image of the left hand, it looks, okay? But if I put a sign here, okay, or if I track these two fingers, when I put them on the top of each other, those two fingers, okay, those two fingers are not sitting on each other. Okay, so my two hands are not really, they are mirror image of each other. They are mirror image of each other, but they are not superimposable. They are not superimposable. Okay, and so again, let's rephrase. We're talking about stereoisomer, and we have molecules that they are mirror image of each other, right, left, right hand. They are mirror image of each other. Okay, but they are not superimposable. What does it mean? When you put them on the top of each other, they're not going to match each other perfectly. Something is going to be off. Okay, in that case, we say you are dealing with, stereoisomers. Okay. And first thing, what's a chirality? How do I get a chiral molecule? The chirality, you will get it whenever you have a center that it has 4 different groups attached to it. So I have a carbon, if we're talking about organic chemistry, we have a carbon with 4 different groups. Like, for example, this carbon, it has OH, H, methyl, and ethyl, completely different groups. When I say different groups, you're talking about different molar masses. Different molar masses. Okay, and so you have 4 different substituent, and we say in that case we have we have like a chiral center. Okay, we have stereo center. Okay, let's zoom on this. If carbon has four different substituents, in that case, you're gonna have stereo center. Okay, what does it mean? That okay, your molecule will be chiral. So the molecule will be chiral. Okay, I'm talking about just one carbon atom, and I have a stereo center, and there is no another group until now. Okay, so I'm gonna say the molecule will be chiral. Okay, it means it's gonna affect the light whenever light is coming to it, and we will talk about that one later. Okay, next. So now that we know we have a stereo center, we're gonna put a star on it, and that means we have a stereo center, or we have a chirality center. Okay, we're gonna put a mirror in the front of it, and then we'll measure distance of those substituent from the mirror. Okay, and try to draw the rest. Okay, and so I'm gonna say I have a carbon and this distance. Okay, it's the same distance as that one. Okay, so carbon is here. Next, I have a fluorine inside the plane. So here you go. This is a fluorine. Then I will have bromine. So I'm gonna say I have a fluorine here, and bromine is there. What else? Okay, now look to, forgive me. Bromine is gonna be this direction, because bromine is gonna be too close actually to the mirror. Okay, so that's gonna be bromine, and here we will have fluorine. Okay, what else? Look to chlorine. Chlorine is gonna be somewhere in this position. So I'm gonna show the chlorine there. This is gonna be chlorine. And where is iodine? Iodine has the longest distance from the mirror. So iodine is gonna be somewhere here, okay? And so we're gonna show iodine. And that's gonna be iodine, okay? And now, what's the relationship between these two? These two are mirror image of each other, but they are not superimposable, okay? And why do I say mirror image? Look to bromine. Bromine on the left side, bromine here on the left structure is on our right hand, while on the second structure is on the left hand. Now, I say they are not superimposable, okay? Again, what does it mean? It means this. It means if I take this structure, okay, if I take this one and move it here, you will see that everything is mirrored, okay? And everything is mirrored, okay? Iodine is on the left, one structure is on the left, here is on the right side. Bromine on the left, we have it on the right side, okay? Chlorines or iodine, chlorines and fluorines are fine, okay? But the rest are mirror image of each other. Okay, so these two, I'm gonna call them non-stereomers. Okay, these two are okay, stereo isomers. Okay, we have two structures. They are mirror image of each other, but they are not. Okay, they are not super imposable. Okay, they are not superimposable, and that means you're dealing with enantiomers. Okay, let's figure whether we have a chiral center or not. Remember, in order to figure there is a chiral center or not, you need to have four different substituents. And this carbon, okay, let's go with this carbon. Okay, why that carbon? Because the rest, they're going to have two hydrogens, and that's going to cancel the chirality. So we don't have a chiral center there. Okay, it looks I have one OH, but if I look this side or that side, I have carbon with two hydrogen, and then carbon with two hydrogens. So until now, those two substituents are identical. What's the fourth one? The fourth one, and you have hydrogen here. Okay. And now, if I keep continuing, I will get exactly same stuff and the same substituent on both sides. So this one is not, okay? This is not chiral, okay? So there is no stereocenter. Okay, so I'm going to say no stereocenter. Okay, we don't have a stereocenter. How about here? Okay, how about this? If you look to the right side, you have carbon. Okay, you have OH, and here there is a hydrogen. And what's the fourth one? The fourth one, okay, again, you see a carbon. But what's the difference between those two carbon? This carbon, it has hydrogen. It has two hydrogens, actually. Two hydrogens. And that carbon, it has one hydrogen and one OH. So those two carbons are not identical. And the reason for it is the OH. Okay, instead of hydrogen, we have OH. And because I see four different groups attached to it, so I do have a stereocenter. And do I have another stereocenter? Here, that one also is a stereocenter. Okay, so we have two stereocenters. I'm going to show them by the stars. And that means we have two stereocenters. Okay, what else? Okay, let's check this. What do we see? We see ethyl, methyl, okay, and entire of this substituent. And last one is going to be hydrogen. We have hydrogen here. Okay. We have hydrogen. So do we have stereocenter? Yes, we do have a stereocenter. So let's show it by dot. There is a stereocenter there. Okay, another one. Okay, another one. Okay, let's talk about this carbon. Okay, what do we have attached to it? We have a methyl. So this is methyl. We have a substituent, that's substituent. And what's the next substituent? Next substituent, entire of this. Okay, those two substituents are not identical. Methyl, of course, is going to be different. And what's the fourth one? The fourth one is going to be hydrogen. Okay, it's going to be a hydrogen. So that one also is a stereocenter. Okay. Left side here, what do we have? We have one substituent here. That's a second substituent here. And we have a methyl. Okay, so three substituent, and three substituents are different. And what's the fourth one? Fourth one is going to be hydrogen. So that carbon is a stereocenter, okay, or chiral center. Okay, next, how about this carbon? How about that one? That carbon is going to have a ethyl, methyl, and entire of this substituent attached to it, and also hydrogen. You have hydrogen attached there, back of the molecule. So that one also is a stereocenter. Okay, and now try to answer this question and see whether we have a stereocenters, and if we have, how many of them. Okay, great job. So the answer for it is going to be 5. Let's find them. You start from here, 1. Okay, next one is going to be here, 2, 3, and you have 4, and that's number 5. Okay, this is not a stereocenter. Okay, this is not, and the reason for it because you have two identical substituents attached to it. Okay, I'm going to stop the lecture here, and I will see you very soon. Thank you very much, and take care.